Hi everyone, I'm Rashmi Vinayak. Today I'll talk about EC cache, which is a cluster cache that uses erasure coding to achieve load balancing and to reduce read latencies. This is a joint work with Musharraf and Jack from University of Michigan and Jan and Kannan from UC Berkeley. Before getting into the talk, I would like to mention that I'm currently expecting with a due date in early November and hence I'm not able to attend OSDI in person. I would like to thank the chairs for accommodating my request to present the talk through this video. And also, thank you all in advance for your consideration. Reading from memory can be orders of magnitude faster than reading from disks and even SSDs. For this reason, many data-intensive clusters employ distributed in-memory caches, or in other words, cluster caches for high-performance applications. An example of such a cluster cache is Alluxio, formerly known as Tachyon, which can be used as a caching layer on top of various storage systems such as Hadoop Distributed File System, Amazon S3, etc. However, just having objects in memory is not sufficient to get good performance. This is due to the various imbalances prevalent in the clusters. There are various sources of such imbalances, one of which is skew in the popularity of objects. Workload traces from Facebook and Microsoft Bing production clusters show that there is heavy skew in the popularity of objects, taking the form of a zip-like distribution. Here, the top 5% objects are 7 times more popular than the bottom 75% put together. It is also typical to have significant imbalance in the background network traffic in the cluster. We analyzed a workload trace from Facebook Data Analytics cluster and observed that in the top of the rack links, the ratio of maximum to average utilization is more than 4.5x with more than 50% utilization. So some parts of the network are more congested than the others, and this varies with time. Similar observations have been made from the traces from other production clusters as well. In addition, there are failures and unavailability events occurring frequently in clusters. In one of my earlier works, we measured failure statistics from Facebook Data Analytics cluster, comprising of several thousands of machines, and observed that a median of more than 50 machine unavailability events occur every day. All these factors lead to imbalance in load in terms of the amount of data served across the servers, as well as degrade read latency performance. Hence, having a single copy in memory is often not sufficient to get good performance. A popular approach employed to address this issue is what is called selective replication. Here, certain amount of memory overhead is used to cache multiple replicas of the objects based on their popularity. More popular objects get more number of replicas cached. Let us take a toy example. Suppose objects A and B are cached on servers 1 and 2 respectively. Let object A get twice as many requests as object B. In this toy setting, server 1 needs to serve twice as much data as server 2, and this degrades the latency of read requests for object A as well. In this case, selective replication caches 2 copies of object A, thus balancing the load and also improving the latency performance. This strategy is employed in data-intensive clusters as well as in key-value stores in many web services. Now let us compare selective replication with other schemes in this cartoon plot. Here on the x-axis, we have memory overhead, so smaller is better. And on the y-axis, we have read performance and load balance, so higher is better. Let's say having single copy cached in memory operates here. It has zero memory overhead, but poor in terms of read performance and load balance. Selective replication uses certain amount of memory overhead in order to improve read performance and load balance. We we present EC-Cache, which is a new cluster caching solution that uses the same amount of memory overhead as selective replication, but significantly improves read performance and load balance. EC-Cache achieves this using a tool called Erasure Coding and employing its properties when serving read requests. Here is a quick one-slide primer on erasure coding to make sure we are all on the same page. An erasure code takes K data units and creates R, what are called parity units. These parity units are certain mathematical functions of the data units. In EC-Cache, we employ codes which have the property that any K out of these K plus R units are sufficient to decode the original K data units. In this example, we have 5 data units and 4 parity units. So we have K equals 5 and R equals 4. Due to the any K out of K plus R property, we can read from these 5 units and decode the original 5 data units, or we can read from these 5 units and decode the original 5 data units. With this context, now let us take a bird's eye view at EC-Cache. At a high level, EC-Cache design is very simple. When writing an object, it is first split into K data units. In this example, we have K equals 2. These K data units are then encoded using an erasure code to generate R parity units, where R is chosen depending on the popularity of the object. In this example, we have R equals 1. These K plus R units are then cached on distinct servers chosen uniformly at random. When reading an object, we need to read at least K of the K plus R units of the object. EC-Cache reads from K plus delta units of the object. That is, it reads delta additional units and uses the first K units that arrive. The K plus delta units are chosen uniformly at random out of the total K plus R units of the object in order to uniformly spread the load across both data and parity units. Suppose we want to read the object X that we just wrote in the previous slide using delta equals 1. So we read from K plus delta equals 3 of its units. For some reason, here the first unit is slow to arrive. We just ignore it and use the other 2 units that arrive first. The K units that arrive first are used to decode the original K data units, which are then combined to serve the read request. So how does erasure coding help EC-Cache in achieving load balancing and reducing read latencies? There are 4 main reasons. First, erasure coding allows for finer control over memory overhead of the objects. Under selective replication, one can either cache a full replica of an object or not, thus allowing us to control the memory overhead only in multiples of 1. On the other hand, erasure coding allows for fractional control. For example, if we choose K equals 10 for an object, each additional parity adds a memory overhead of only 0.1, thus allowing us to control the memory overhead of that object in multiples of 0.1. Second, by splitting an object and caching them on different servers, EC-Cache is reading smaller amounts of data from each of the servers. This allows for more smoothly spreading the load across the servers. Under certain simplifying assumptions, we show that the variance of the distribution of the load in terms of the amount of data served across the servers decreases K-fold under EC-Cache as compared to selective replication. Splitting the objects and reading from multiple servers also helps in reducing median latency as it provides read parallelism. However, this severely hurts tail latency as reading from multiple servers involves higher probability of hitting stragglers. This is where any K out of K plus R property comes to the rescue. By reading from just 1 or 2 more units than the K needed and using the first K that arrive, helps in mitigating the negative effects on the tail latency. Now let's look at design considerations in EC cache and contrast them with storage systems where erasure codes have been traditionally employed. In storage systems, erasure codes are employed primarily to provide fault tolerance in a storage efficient manner. On the other hand, EC cache employs erasure codes in order to load balance and to reduce read latencies. Now let us look at the choice of erasure code. In storage systems, reconstructing failed or otherwise unavailable data units is a frequent operation, and it consumes significant amount of network bandwidth and device I/O. For this reason, many storage systems employ codes that are specifically designed to optimize resource usage during reconstructions. Some of these codes do not possess any k out of k plus r property. On the other hand, EC cache is a caching layer, and there are no reconstruction operations in this layer as data is persisted in the underlying storage layer. However, it is critical that the code possess any k out of k plus r property, which helps in load balancing and reducing latencies when serving read requests. Now let us look at the choice of whether to encode within objects or across objects. That is, whether to split objects to create the data units for the erasure code or to use different objects as the data units. Among storage systems, some systems encode within objects and some encode across objects. This does not make a difference in terms of fault tolerance, which is the primary purpose for which erasure codes are employed in storage systems. On the other hand, in EC cache, we need to split objects and encode within objects so that we can spread the load across both data and parity units when serving read requests. If we encode across objects, there is very high bandwidth overhead in using parities to serve read requests. We have implemented EC cache on top of Alluxio, which is a popular cluster cache. The backend caching servers are unaware of erasure coding, and the EC cache client library handles all the logic involved in reading and writing objects. We employ Reed-Solomon codes, which provide any k out of k plus r property, and use Intel ISAL hardware acceleration library for fast encoding and decoding operations. We have performed extensive evaluation on Amazon EC2 with 25 backend caching servers and 30 client servers, each issuing several thousands of read requests. For object popularity, we use ZIF distribution with high skew, which is shown to mimic the real-world object popularity distributions well. EC cache uses the parameters k equals 10 and delta equals 1. That is, it has 10% bandwidth overhead as compared to selective replication when serving read requests. We have performed evaluations on varying object sizes. I'll start with results on objects of size 40 megabytes. First, let us look at load balancing. In both of these plots, on the y-axis, we have the load on the servers in terms of the amount of data read, and on the x-axis, we have the servers sorted according to the load. We can see that EC cache provides much better load balancing as compared to selective replication. A standard way of quantifying load imbalance is through percent imbalance metric, which compares the maximum load to the ideal average load. We observe that EC cache provides threefold reduction in load imbalance metric as compared to selective replication. Now let's look at read latency. Here on the y-axis, we have read latencies, and on the x-axis, we have different percentiles of the read latencies. The black bars correspond to selective replication, and the gray bars correspond to EC cache. We observe that EC cache provides more than 2.5-fold reduction in median latency and more than 1.75-fold reduction in terms of tail latency. Now let us look at varying object sizes that are shown on the x-axis of these two plots. We observe EC cache providing significant gains in terms of median latency as shown on the left as well as in terms of tail latency as shown on the right. The gains provided by EC cache increase as object sizes increase. For instance, for 100 megabyte object sizes, EC cache provides more than 5-fold reduction in median latency and more than 3-fold reduction in tail latency. Now let us look at the key role that delta additional reads play in reducing tail latencies. Here, we have shown the CDF of read latencies, and we have 3 curves, one for selective replication, which is in green on the right, and 2 curves for EC cache with and without additional reads, that is with delta equals 0 and delta equals 1. We see that the 2 curves for EC cache are almost identical until we reach the tail, where we see a significant degradation in tail latency when there are no additional reads. We have additional evaluations in the paper in the presence of background network imbalance and in the presence of server failures. We also provide evaluation of the write performance and sensitivity analysis with respect to all the parameters. In summary, we presented EC cache, which is a cluster cache that employs erasure coding to achieve load balancing and to reduce read latencies. So far, erasure coding has been largely employed in disk-based storage systems, primarily to provide fault tolerance in a space-efficient manner. EC cache demonstrates a new application and new goals towards which erasure coding is highly effective. We have implemented EC cache on top of Alluxio, and through extensive evaluations on Amazon EC2, we show that EC cache provides significant gains in terms of load balancing, as well as in reducing both median and tail read latencies. With that, I will end my talk. Thank you all for your attention.